This is question 4 on the 2020 higher level mock about a satellite in orbit around the planet Mars. Starts out with a definition that is about as common as a pink shirt on a physics teacher on a Wednesday. The definition involves, for gravitational field strength, involves two parts. The first is the fact that it's the force per unit mass, where the per unit mass is essential, and then the notion that that mass is a test mass or a small mass that is used to determine the gravitational field strength. The next part may have caught you by surprise, where you have to explain why it is reasonable to approximate Mars and the satellite both as point masses. The answers are slightly different for each. For Mars, because it's spherical and symmetrical, it does work out that you can assume all of its mass exists at its center. The answer for the satellite is that it is very small in comparison to Mars, so it is effectively a point mass when compared to the size of Mars itself. Moving on to part B, you're given a Kepler's third law here and asked to find the constant of proportionality given the information. So you're going to use the data booklet formula for the speed of an object in orbit around a planet of mass m and with orbit radius capital R, and we also need the fact that the speed in the orbit is equal to the circumference over the time to travel that full cycle. So setting these two equal to each other and solving for t, working it through, you can get this relationship between t and r. You can see the t squared r cubed relationship. Therefore, 4 pi squared over gm is k, and then it is a case of substituting in the given values to get a value for k. Notice that although there is only one significant figure given in the question, you're required to show more than that in your answer here, and that's quite common on show that questions. They want to see that you have actually done the calculation and not just taken this answer down. So always show extra digits on show that questions. And then the last part asks you to find the orbital speed of the satellite. So we can use this equation again from the data booklet, but before we can do that, we need to know what the radius of the orbit is. We can use the information from the original relationship, now that we know the k value from above, to find the radius, and then it's just a case of substituting the radius into the orbit equation to find the orbital speed.